There's one more category of indeterminate forms that can spring up that we should have a look at. Like the product and sum indeterminate forms that we looked at last time, you can't use L'Hopital's rule for these indeterminate forms directly, but you can convert these into the 0 over 0 or infinity over infinity indeterminate forms and then use L'Hopital's rule. So let's have a look. Let's evaluate the limit as x goes to 0 from the right of tangent of 2x to the power of x. So if you just try to plug in 0 by sort of naively taking a limit as x goes to 0 from the right, so in our base here, tangent of 2 times 0 is tangent of 0 is 0, and the exponent x just also goes to 0. Now this might look like it's not an indeterminate form because, hey, shouldn't it be 0? But the base, if you think about raising 0 to a power, the base is trying to make this 0, because if you raise 0 to most powers, you just get 0. But raising anything to the power of 0 should give you a 1. And so this expression, it's sort of trying to be 0 and 1. And since you can't tell which one wins, this is indeterminate. So 0 to the 0 is an indeterminate form. There are actually two other indeterminate forms that involve exponents. There's infinity to the 0. And this is indeterminate because the large base is trying to make this infinite, but the power of 0 is trying to make this equal to 1. And then the final indeterminate form involving exponents is 1 to the infinity. And this is an indeterminate form because the base being 1 is trying to make this 1, but the exponent being large is trying to make this large. So in these three situations involving exponents, you can't tell what value you get without doing some sort of more sophisticated computation. All right, so let's see what we can do. So we're calculating the limit as x goes to 0 from the right of tangent of 2x to the power x. All right, so we know we can't use L'Hopital's rule directly because we don't have 0 over 0 or infinity over infinity. And you know, because the variable x shows up in the base and the exponent, you might think, well, this is a calculus class. Shouldn't we be writing this exponential base e? And of course, you'd be right. So let's do that. This is the limit as x goes to 0 from the right of e to the, so we're just going to write the base, tangent 2x, base e, and tangent 2x is e to the natural log of tangent of 2x. Okay, let's rewrite this just a little bit using exponent rules. So this is the limit as x goes to 0 from the right of e to the x times the natural log of tangent 2x. All right. Now because the exponential function e to the something is continuous, this limit on the outside, we can actually move into the power. So this is e to the limit as x goes to 0 from the right of x times natural log of tangent 2x. All right. So we've rewritten our original limit in some other way. Let's see if we can evaluate it now. If we just plug in 0 as x goes to 0 from the right, x becomes 0, and tangent of 2x as x goes to 0, tangent of 0 is 0, and the natural log is going to minus infinity. So now we're in a situation where we have a 0 times infinity indeterminate form. We still can't use L'Hopital's rule directly, but we know how to handle this situation. Rewrite the product as a quotient so that you get either 0 over 0 or infinity over infinity. so we have to either shuffle this x down into the denominator or shuffle this natural log down into the denominator. And it's going to be a lot easier to differentiate if we move the x into the denominator. So this gives us e to the limit as x goes to 0 from the right of natural log tangent 2x over 1 over x. All right, and now just to check again, what we get by taking the naive limit at 0 is infinity over infinity, negative infinity over infinity. So still indeterminate, but now it's an indeterminate form where we can use L'Hopital's rule. So this is e to the limit as x goes to 0 from the right. Okay, now we do L'Hopital's rule. Take the derivative of the numerator and the derivative of the denominator separately. So in the numerator, be careful about the chain rule. This is 1 over tangent 2x times the derivative of tangent 2x, which is, let's see, derivative of tangent is secant squared 2x. But then we have to multiply by the derivative of 2x, which is 2. Okay? And then in the denominator, the derivative of 1 over x, remember 1 over x is really x to the minus first, and the derivative of x to the minus first is minus x to the minus second. All right. So this is e to the limit as x goes to 0 from the right. Okay, let's see. This tangent actually belongs in the denominator. These x's in the denominator actually are in the numerator because it's to the negative powers. And also we have a minus sign and a 2. So minus 2 times x squared times secant squared 2x. Okay. Now, if you evaluate at 0, we're still getting 0 over 0. So you might think, well, we should use L'Hopital's rule again, but the derivative of the numerator is going to get really bad, and also the derivative of the denominator is going to be also pretty bad. So instead of taking the derivative again, let's try to simplify even more. Remember, secant and tangent, these both have lots of sines and cosines hiding inside. So let's write everything in terms of sine and cosine. Because I expect that there will be some canceling and simplifying that we can do. So we get a minus 2x squared times, so secant squared, that's 1 over cosine squared, 2x. And then down here, this tangent is sine over cosine. So sine 2x over cosine 2x. All right. So this is e to the limit as x goes to 0 from the right of minus 2x squared. Let's see, in the numerator, this cosine down here is going to flip up to the numerator. The cosines, so this one's going to end up in the numerator. This cosine squared, it's in a denominator, so it goes down here. So we get cosine 2x over cosine squared 2x times sine 2x. Some of the cosines cancel. Let's see, this cosine cancels one of those cosines. So we get e to the limit as x goes to 0 from the right of minus 2x squared over cosine 2x times sine 2x all right. And things don't look great at the moment because if you just plug in 0 in this exponent, you still get 0 over 0. Okay, so that's annoying. But this denominator, cosine 2x times sine 2x, that's part of a trig identity. I remember that for a product of a sine and a cosine, there's a trig identity for that. And you don't necessarily need to remember what the result of that trig identity is, but you should definitely remember that there is such a trig identity, just so that you know to go look it up when you need it. So if you look up the product to sum identity for cosine times sine, what you'll get is, I guess it's actually a double angle identity. Cosine 2x times sine 2x is 1/2 cosine of 4x. I'm sorry, that can't be right. It's 1/2 sine of 4x. That's better. Okay. So still 0 over 0, but now doing L'Hopital's rule again is going to be pretty straightforward. So let's do L'Hopital's rule again. E to the, this limit, all of this algebra is happening in the exponent here. Limit as x goes to 0 from the right. Now use L'Hopital's rule, so we get minus 4x over, and then in the denominator, the chain rule is going to spit out a 4, and that cancels the 1/2 and gives us a 2. Derivative of sine is cosine 4x, and I already got the 4 from the chain rule. All right, well, finally, when we evaluate this at x equals 0, we get something that isn't an indeterminate form, finally. So 4x, when you plug in x equals 0, you get 0. And in this denominator, 2 times cosine 4x, when x is 0, that's 2. So this whole thing is e to the 0. In other words, it's 1. Okay, finally. So as with the other indeterminate forms, so this particular indeterminate form was 0 to the 0, but for any of these exponential indeterminate forms, 0 to the 0, infinity to the 0, or 1 to the infinity, handle them all the same way. Just take your base, convert it to base e, and that will give you a product in your exponent, and that product will be indeterminate. And we know how to handle indeterminate products, convert it into an indeterminate quotient, and then you can use L'Hopital's rule. So actually using L'Hopital's rule in this particular example turned out to be a little tricky. We had to use L'Hopital's rule once, right here. So that was L'Hopital's rule once. And then we did a bunch of algebra, and then we used L'Hopital's rule again right here. And it also, we had a trig identity right there. So kind of a lot going on in this one. But the general idea is, if you have an indeterminate exponential, switch to base e, now you have an indeterminate product, and then convert the indeterminate product to an indeterminate quotient and use L'Hopital's rule.